So don't say anything too compromising because we are recording. There you go, there's a laser on there as well.
I will try to not wet too much. I love cheese. Was there anyone else in the lab that's coming in the room?
One person in the lab.
Should I put a glass of water for you?
Which one is the first one? Is that the light?
That's the Oxide, which but it's now used.
That was also this kind of advanced shows.
Yes, you start just
before Craig's.
What should we start on now? I think that's all.
Yeah, I think you could start.
Yeah. Well, let me introduce you. Dr. Russel Binions completed his first degree in chemistry from the College of St. Hild and St. Bede, the University of Durham, in 2001. He subsequently completed a PhD in 2005 at University College London. He spent a year working in industry for the Novel Optical Group before returning to UCL in autumn 2005 to complete postdoctoral positions working on thermochromic thin films and zeolite modified gas sensors. He was awarded a Royal Society Dorothy Hodge Fellowship in 2008. Dr. Binions is currently a lecturer in functional materials in the School of Engineering and Materials at Queen Mary, University of London, and an honorary senior research associate at UCL. He is the author of over 80 peer-reviewed journal papers, 6 book chapters, and 1 book. His research interests encompass new chemical vapor deposition techniques, metal oxide semiconductor materials, gas sensors, energy materials, photocatalysis and related areas, chromogenic materials, nanocomposite films, and energy-efficient building materials. Dr. Russel Binions.
Thank you, Azad. Thank you for the introduction and indeed the invitation from yourself and Paul. So yes, I'm going to, I'm mainly going to tell you about, I'm mainly going to tell you something about electric field-assisted chemical vapor deposition, which is something that I started working on in my research fellowship and have continued to do subsequently. But that's not all I do. This is a kind of rough diagram which sort of talks about all the different bits and pieces that my group's involved in. We're mainly interested in thin films and their use as sensor materials. We do a whole range of different techniques, not just CVD, do a lot of solution chemistry too. And most of my research is focused in practical areas. I'm interested in solving real-world problems rather than sitting in my ivory tower plotting how to take over the world or what have you. One of the things that we've recently been getting into is supercapacitors, energy materials, and photovoltaics as well. And I'm actually going to talk something about that. So I'll say something about electric field-assisted CVD, what it is, why it's something that may actually matter a little bit or can do something. I'll talk about it, how we apply it to energy efficient glazing, particularly thermochromic glazing. I'll say something about some supercapacitor electrodes, some metal oxide gas sensors, something very briefly on the using photocatalysts, and then if there's time, I will say something very, very briefly on some of the work on photovoltaics that my group has been doing. This is mainly because I got some results this morning which made me smile, and I'd like to share them. So anyway, never mind, electric field assisted CVD. Well, I guess I don't need to spend an awful lot of time going through what chemical vapor deposition is to you guys. I think you're probably all more than aware. But just to run through, okay, you've got some precursor molecules, they absorb on the surface, okay, they have some migration on the surface, maybe some nucleation, okay, we'll lose some part of our molecules, byproducts or what have you, we'll get film growth, and all the time losing some byproducts, ligands or what have you. And this is great, this is the classical view. Notice that there is a single thing mentioned about this gas phase and what's happening there. So, in classical CVD, we basically ignore any gas phase species. Now, I'm sure any of you who have ever thought about CVD will understand that, well, it makes life a lot easier if indeed you do it. However, there's lots of different things going on, without doubt. And at least some of those species are going to have some kind of dipole or charge or what have you. And if we apply an electric field, we should see some interaction with those species. Okay? Now, if we have some interaction, we're going to change the kind of growth and nucleation maybe that we have on our substrate, and if we can change those the structural properties that they have, then we'll see some changes in the functional properties as well, or at least that's what I'm going to tell you or try and get you at. Okay, so just how might this happen then? So this is all very hand-wavy theory. This is one of my favourite kind of ligands, and I'm sure you're all aware, the beta-diketonate type things. Okay, and in this case it's a vanadile type ligand, and we have some permanent dipole along this vanadium oxygen axis, which I'm going to represent in my cartoon with this yellow triangle. Okay. Now, normally what you would expect to happen with your gas phase species coming into your reactor is they're going to be tumbling around, random orientation and whatnot. Okay. The first thing that we might expect to happen then is if you apply a field, okay, you would reasonably expect that there might be some alignment. Okay. The negative end of the dipole is going to be attracted to our positive substrate or the positive bias, and vice versa. We might also expect to see some movement towards or away from our substrate surface. This depends a lot on the relative shielding effects from the substrates and indeed the precursor itself, but there certainly could be some dielectrophoretic acceleration. Okay, there could also be a surface effect. So one of the things which is clear is that if you're growing a metal oxide, like the type of things I'm interested in, they have very different permittivities than our gas phase will have. This means that we're going to have a difference in the localized electric field, and we could lead to having some very strong surface dipoles, which could lead to the selective attraction of some of those charged gas phase species, and ultimately to some kind of pseudo-dendritic or hierarchical or nanowire growth or something like this is also possible. The other thing which is also possible, bond activation. Okay, got an electric field pulling it either end of our molecule, of our dipole. Maybe we're pulling that apart, we're reducing the activation energy for some reaction on our surface. Okay, so these are the kind of ideas that I have about how these electric fields can interact with our species. I'm sure there are a number of other possibilities as well, which I'm always open to. So everything I'm going to tell you today then is based around an aerosol system. Again, I don't think I need to go into too much detail. All of our reactors are cold wall quartz type things, and what essentially we're going to do is we're going to add our substrate and top plate will be TCO coated pieces of glass, which we get from Pilkington glass, and we're going to use those as our electrodes in our system. Otherwise, it's a completely normal bog standard aerosol type CVD system, and you can do this for atmospheric pressure and reduced pressure systems as well. We've done quite a lot of work in atmospheric pressure, which we're currently in the process of trying to patent, so I'm not actually going to tell you anything about that, but certainly the aerosol stuff should be hopefully interesting. Okay, so energy efficient glazing then. So how can this help here? Well, we have a bit of a problem, and it's not just me taking selfies on London Bridge. Okay, increasingly we've got big buildings like this, this thing which is known as the walkie-talkie in London. You know, big glass-fronted buildings. You cannot build high, tall buildings out brick and you know, standard windows or whatever, because at some point they'll get too high, you get a gust of wind, actually they'll fall over, they're not reliable. So if you want to build things this high, you need to use steel and glass. The only problem is, steel and glass, or glass in particular, it's not very good at insulating. But also this is a problem for residential housing. Okay, this is a kind of heat map of a standard residential house. You can see the difference in the temperature if you've got an energy efficient window. These are ones with low emissivity coatings in winter. You can see that they're much better at keeping the heat in or what have you than uncoated windows. Okay, so there's a question about energy here. Okay, so we've got more of these big glass fronted buildings being built, as well as obviously issues with residential property. Okay, we can't really use traditional insulation methods on these kind of skyscrapers and whatnot. Okay, because there's not much ceiling, and you certainly can't put wall cavity insulation in a window. It kind of defeats the point of having a window, I suppose. Okay, so this means that we have an increase in the need to heat and air condition our buildings. Okay, so more CO2 being generated, higher energy bills. Okay, so if we can use energy efficient glazing, not only are we going to reduce our emissions, actually, probably more importantly, we're going to save some money. And that seems to be, in this world at least at the moment, a better reason to do anything rather than saving it for future generations. But anyway, never mind about that. So this is just a diagram of the solar spectrum. I've arbitrarily split the infrared up into near and far. Of course, 1200 nanometers to 2.5 microns is not really the far infrared at all. I just really want to make the point that in about the approximately 50% of solar heat gain that comes in the infrared, actually only about 10% of it comes in this area above 1200 nanometers. And this is one of the big challenges that hopefully I will get across to you as we go on. Okay, so what existing products are there? Well, there are solar control heat mirrors. These are going to strongly reflect in this near infrared region. Okay, so your heat gain's not going to go into your building. Okay, it'll stop your building getting hot. And that's great. Typically, they're made of very thin films of silver or metal alloys or what have you, and they're produced by sputtering. Now, the problem with that, of course, is that, well, PVD deposited films don't tend to have the lifetimes that we would like for windows in the building. Okay, there's also low emissivity type glass such as K-glass. Okay, they will reflect in the far infrared, so I'm talking about the 5 to 50 micron region, and that basically stops re-emitted radiation, black body radiation, from escaping in a building. Okay, and that's also very good. There's also absorbing glass as well. Typically this is coloured, and this will absorb not only in the visible region and in the near IR. Okay, and in this way, well, actually you're not preventing your energy from entering the building, but you are changing the timescale that it enters. So in effect, a lot of that energy will be re-radiated when the building's not occupied, if it's a building like Canary Wharf or a big office building, what have you. Okay, so this is all good. So there are these products. So why do we need to worry about this? Why am I concerned? Okay, well, a couple of years ago, not only did Mel Smith pass away, but there was this article on the BBC website. We've got to the point where we're so good at insulating our homes that we're actually creating other problems. In the summer, people who are the most vulnerable with respiratory illnesses or the elderly are basically having to suffer from homes which are far too hot. Because we're very good with, the building codes in the UK stipulate that you must have some kind of low emissivity or energy saving coating in your glazing when you build a new house, which is great. In the winter, fantastic. The energy will come in, can't leave, so it stays nice and warm. However, in the summer, even more energy comes in, and that can't leave, so it just gets hot. We're basically turning our houses into greenhouses, and this is true of residential buildings as it is of office buildings. So actually, these kind of static coatings, which only prevent one type of radiation coming in or leaving our buildings, is really probably not actually a very good answer. So what do I want to do? Well, I want to use thermochromic glazing. So this is glazing where the properties will change depending on the temperature. So here's an example of one of my group members working hard on a autumn or winter's day, and you can see you've got your energy from the sun, and whilst you've got a lower temperature, okay, all of that solar heat gain, that energy, you're going to be able to come in to the office and help keep it a little bit warmer. Okay. However, if it gets a bit sunny, rarely happens in the UK, but let's say theoretically. Okay. Now what's going to happen is some of that radiation is going to be reflected away. Okay, and we're going to still maintain, hopefully, a nice ambient working temperature, so the student can continue working just as hard as they always have done. So that's kind of the idea. So what's this based on? Okay, well, thermochromism in vanadium dioxide, which is the principal material we want to use, it's based on this structural change from a monoclinic semiconducting form to a metallic rutile form. Okay, and just to draw a little cartoon, essentially what we have in the monoclinic form then is we've got some overlap of these DZ squared orbitals, which essentially, when you look at the band structure, get filled by various electrons, and you have essentially, well, it's not an insulator exactly, but a material with quite a sort of relatively low band gap, 2.3 electron volts or so. Okay, when you get warmer, you get some disruption in the crystal structure when you go to the rutile phase, and suddenly you no longer have this overlap of these DZ squared orbitals, so you lose that band from your band structure. Okay, so these electrons, they become free, but they have to go into a different band in your structure. They don't quite fill it, so you get metallic behavior. Okay, and so this, along with this, you get some enhanced infrared reflection, although relatively little or negligible change in the visible portion of your spectrum. So great. Game theory. So there are three big questions about this. One of the reasons, or the three reasons that vanadium dioxide hasn't really been taken up. First is transition temperature. Okay, single crystal vanadium dioxide has a transition temperature of 68 centigrade. If we have to get a building or a surface on the building that hot before we see a change, then well, we're all probably going to be quite dead. So we need it to be a little bit less than that. And there have been approaches done using metal doping. Tungsten, niobium are particularly good at this. A couple of atom percent incorporation of tungsten, for example, will drop that transition temperature down to somewhere around 22 degrees centigrade, where you might actually want it. There is a problem with that, which I'll explain in a moment. Also, we can grow films with some strain, some preferential orientation, and we can lead to a change in our transition temperature as well. And we can actually do some of that by controlling our crystallite size. Okay, the big problem then for metal doping comes with this thermochromic efficiency. Okay, inevitably there's some hysteresis to this transition. And one of the things that metal doping does is it changes the width and gradient. So actually this becomes a wider transition and a more gradual transition with metal doping. And actually that's not so good. We also have another issue. Okay, so about 40% of our infrared radiation is going to come into our building or from the sun between 700 nanometers and 1200 nanometers. How do we maximize the transition in that part of the infrared? Because actually the bit between 1200 and 2500 nanometers is small. Okay, we can modulate as much as we like, but it will have very little effect. The other issue is film color. Vanadium dioxide is unfortunately a pretty grim-looking browny yellow color, and no one in their right mind would want it on their window. So there's been some approaches that we've looked at, and other people have looked at, incorporating gold nanoparticles and taking advantage of the surface plasma resonance of those to change the color is one way, or you can look at magnesium and fluorine doping like Granqvist's group in Uppsala University have done, shift the band edge into the visible, and you have much nicer looking film. So there's some answers to that. Okay, so well, what should we be aiming for in terms of our transitions? Okay, we know that we can see some kind of change, and we know that we can have some kind of width, gradient to our transition, whatever. What do we actually want? Well, we decided to approach this by doing some modelling. Okay, and essentially we used a bunch of ideal spectra based on things that we thought were achievable in the lab. Okay, and we've set some arbitrary targets such as visible transmission is set to 65% and various different things. And in the initial work, we didn't worry too much about the hysteresis effect. Okay, so our model is also like this kind of thing here. We're looking at double glazed window unit, standard 4mm float glass with a 12mm gap, filled with just air. Our vanadium dioxide film is put on the surface too, so that's this inside surface of our exterior pane. And we're going to base all of our transitions and changes on the actual surface of that piece of glass, which is something not everyone does. It can be a little bit misleading. Okay, so 2 samples. Okay, these are standard shoebox models, a 6x5 by 3 meter box. Okay, with some arbitrarily defined area as the window. So for the commercial example, what we described is 9%. For a residential scenario, it's about 25%. Okay, and this is, I should probably stress that all of the numbers are not, that I'm going to show you, are not, they're useful for comparative purposes, but, to say that this, that, the other saves you 100 kilowatt hours per year, okay, is going to be, that's essentially a meaningless statement to regard it as that. Anyway, so these are the kind of spectra that I'm talking about. So we've got some kind of fixed transmission, okay, and then if we've got a 6% change in transmission, this is what we're talking about. Our transmission will go from lower temperatures and reduce down at higher temperatures, and then there will be a corresponding change in reflectivity as well. Okay, so just show some. Oh, we also compared against a couple of industrial standards. This one here, E, is a silver sputtered glass, and on the right is a body tinted absorbent glass, which is blue in colour. So just to show you then some initial results from this. Okay, we see the static coatings here. So this is our silver sputtered glass, and this is our blue body tinted glass. And this energy consumption improvement is relative to a plain double glazed window under the same conditions. And essentially, there's a couple of things you can see. Is that if you have a high transition temperature, okay, well actually it doesn't help things very much. What we really want is low transition temperature, about 20 degrees, and we want as large a transition as possible. Okay, and that makes sense because it's giving you the opportunity to modulate as much solar heat gain as possible. Okay, we then looked at some great hysteresis gradient effects. So how sharp is our transition? Is it very sharp like this? This line here, so it says changes by 0.1 degrees, a 10% drop in transmission per 0.1 degrees, or a more gradual transition. Okay, if we look at those, we can see that, again, the sharper our transition, the better our energy performing or energy saving behaviour ought to be. Okay. Again, if we look at hysteresis loops, so in this case we've chosen a fixed gradient for our transition, and we're just looking at, is our gradient 5 degrees, 10 degrees, 15 degrees, or what have you, and we're going to look at different transition temperatures. And what we can see is that, okay, we want to have a very narrow hysteresis width, and we want a lower transition temperature again. Okay, quite whether we can produce a hysteresis width of 0 is a good question, but we'll come to that. Okay, combine all these things together. Okay, we find out that we get, this is our kind of optimum thing. So very low hysteresis width, very sharp gradient, low transition temperature. Those are the things we want to aim for. Which basically what I'm saying here. Okay, so we can get potentially an additional energy benefit of about 50% compared to a normal double glazed unit, and perhaps another 10-15% compared to industry standards. Okay, but actually, I think one of the things I want to point out is if we can get close to this ideal behaviour, actually we're still going to have quite a significant benefit. Because I mean, even if it's a 2 or 3% benefit, okay, in terms of the cost over the lifetime of a building, that's actually very significant. But anyway, okay, so some observations. This is from work we did a while back, actually, when I was a postdoc. We grew some vanadium dioxide films, we changed the growth rate, and we can see some structural changes in our electron microscopy. Okay, we can also see some changes in our X-ray diffraction. You can quite clearly see that some of the relative heights of these peaks is changing. Okay, this is some strain-induced preferential orientation. Okay, and as a result of that, we see some changes in our hysteresis behaviour. So, for example, the films which have grown very slowly have got this very wide hysteresis, okay, and it's quite a slow transition. And if we take the midpoint of the biggest change, okay, our transition temperature is something like 65 degrees centigrade. And if, for example, or if we take the contrasting example where we've this green one, we've grown it quickly, okay, the transition width is much slower, and the gradient is a little bit sharper, and also our transition temperature has been reduced. So, okay, the take-home message is that there is this structure-property relationship for thermochromic vanadium dioxide thin films. Okay, so the idea is that if we can manipulate our film structure enough, then we really ought to be able to produce films which have the near ideal properties that we've outlined from our modelling. So how are we going to do that? Well, electric field assisted CVD, obviously. Okay, so I've talked about the setup already. We're using standard solution, 0.1 molar vanadiol ACAC. Okay, we're keeping our gas flow rate and our substrate temperature the same. We're just going to look at differences in deposition time and in electric field strength. We've previously worked out that these are essentially the best conditions to grow vanadium dioxide films. So, what happens? Well, if we don't apply any sort of field, we get this kind of normal, sort of fairly standard island growth, kind of agglomerations and gradual growth a bit as things go on. If we apply, in this case, this is an alternating electric field at 50 Hertz. You can see that as we increase our electric field, okay, we start to see some different kind of pseudo-structuring, and then at some point we see a change in our growth mechanism, and we see something completely different. Okay, again, if we look at a fixed field, in this case positive substrate bias, we can see that we get certain morphologies, and at some point again the growth mechanism is going to change, and we see something else. And likewise, if we change the substrate bias, we see something different yet again, and again at some point we see a change in our growth. So I'm not going to talk too much about why this happens. Discuss that later if anyone wants to. I just really want to point out that we see some quite big changes in our structure. So we can expect some large changes in our properties, hopefully. Another thing that's worth pointing out, we look at this X-ray diffraction patterns. If we have our bog standard deposition, okay, we see growth in the usual monoclinic space group, fairly sharp peaks or what have you. Okay, we grow with an electric field. The first thing is that, well, we're crystallizing in a slightly different monoclinic space group, one that's normally associated with doping. Our peaks are getting broader, which is indicating that we've got a smaller crystallite size, and there's some change in their peak position, which is indicating some change in our lattice constants. Unfortunately, we don't get enough peaks in our X-ray diffraction to really make any significant claims about how the cell volume or the lattice parameters are changing, other than to say that, okay, a shift towards zero would tend to indicate a larger unit cell. But like I say, that's we can't say that. We can't really say that with any confidence because we don't have enough peaks to really do a meaningful calculation. But anyway, again, things are changing based on the application of these electric fields. Okay, look at some Raman. Okay, we can see that we've got some vanadium dioxide present, which is good. We've also got some V2O5. This is pretty normal for vanadium dioxide. Vanadium 4+ is not a very stable ion, and it will oxidize readily. But however, if we do some XPS, okay, we can see that we've got multiple vanadium environments at the surface and indeed corresponding oxygen environments. If you do some etching, this tends to tidy up into a single peak. So the bulk of our material is vanadium dioxide. Okay, we look at the thermochromic properties. These are a little bit of a mess. Okay, we can see that we've got some change in transmission and some corresponding change. Well, actually, the reflectance data is not really particularly useful because we're depositing onto fluorine doped tin oxide, which starts to have some reflective behaviour in the infrared. So this, I'd take the reflectance data of a pinch of salt, but definitely a change in the transmission. So we've made all, yes. However, when we started to look at some of the hysteresis behaviour of some of our samples, we saw this. Okay, we start heating, we look like we're going to have a very sharp transition, very low transition temperature, but when we start cooling our films again, actually what we find is we've converted them to V2O5. And obviously that's a bit of a problem. Some of the crystallite sizes in the films that we've been producing are 3 or 4 nanometers, it's at least from the Shearer equation, which again you can, I think, probably trust about as far as I can throw this bench. But certainly there's some very, very small crystallites, and they're being oxidized. So look at some slightly larger ones. Okay, in this case we can see there's some cycling behaviour. Okay, we've got a reduction in our transition temperature, although nowhere near where we would like it to be, and our gradient is still much wider than we'd like. Okay, well, just to summarise this, we've got some more plans to go forward. Ideally, our thermochromic films will have these incident sharp transitions, low transition temperature. There is some room for imperfection, but we haven't quite got there yet. But we do believe it's possible to make films with the appropriate properties. Now, this is perhaps a little bit of a bold statement, but we think it's possible to lower our transition temperature using EA-CVD. However, we need to protect our nanostructured films to try and avoid this oxidation and keep this thermochromicity alive. And we've been doing some work looking recently with capping layers and the like to do that, but I haven't got those results to show you today, I'm afraid. Okay, so I'm going to go and move on and say something about supercapacitor electrodes now. Okay, well, why are we interested in supercapacitors? High power density. They're essential for assisting low torque electric motors. So they actually find one of their biggest uses in electric buses, particularly in China. Okay, so yeah, things like this. Okay, ruthenium oxide tends to be the gold standard, or perhaps that should be the ruthenium standard. It has very high specific capacitance, but is also very expensive. You can also use carbonaceous materials. There's been a lot of work on graphene and graphene oxides for this area. Okay, they tend to be reasonably cheap, but they don't tend to last very long, and they don't have as high a specific capacitance as we would like. So we thought, well, we've got some interesting microstructures, seem to have some high surface areas. Vanadium oxide can do some redox chemistry, so why don't we give this a try? Okay, these things are cheap and easy to make. The specific capacitance is not going to be as high as ruthenium oxide, but the vanadium oxide should be rather more durable. Okay, just show what we mean. So ultracapacitors or supercapacitors, high power density, relatively low discharge time. Okay, useful. So we grew a bunch of films, and you can see here the. Oh god, that's not coming out right, is it? This top layer should be plus rather than minus. Okay, and again, you can see this on these little metal substrates. Okay, we can make a whole bunch of different structures that seem to be something a little bit more higher surface area than the bog standard AA-CVD grown film. Again, you see an X-ray pattern which is indicative of a large crystallite size, or sorry, a small crystallite size. Okay, under various conditions, then we can get structured growth. So this is our bog standard AA-CVD, and this is one of our films where we've got some kind of structuring, some sort of pseudo hexagonal type thing going on. Okay, now this can lead to a massive increase in surface roughness. Okay, in this case, I think we've going from about 28 nanometers RMS to 85, but I suspect that in the AFM the tip can't quite get down to the bottom of some of these features, so I imagine it's actually rather a lot more. But nonetheless, one of the things we can do then, these two samples, is we can get non-UV induced superhydrophilicity. Now this is really important for supercapacitors because what we're essentially looking at is the accumulation of charge in the Helmholtz layer, and the better wetting you have with your electrolyte means you can have more of this essentially, so you have a high capacity. So this is one of the reasons we think these work reasonably well. Okay, now some guys at the University of Surrey actually prepared these devices and tested them for us. So I'm not going to say too much about that, but just to show a bit of the testing. Okay, this is up to 1,000 cycles, and we can see that these things are broadly rectangular, which is the kind of ideal capacitor behaviour. There's some evidence at the ends of the cycling of some changing or some destruction of the electrolyte. Okay, which is why we get these large peaks, which is not exactly where we want to be, but still a lot better than many other things. And we can see that as a result, the certificate capacitance will fall off. In this case, it goes down to about 500 microfarads per square centimetre from where it started off as 1600. Another example then, oh no, this is different. So this was different scan rates. And one of the things which is very common with supercapacitors is you kind of see some significant tilting away from this rectangular shape, and that tells you something about how easy or how quickly you can get charge from one place to another. And even at very fast scan rates, we still have quite flat CV curves, which indicates that we have very fast insertion and desertion times for our charge. And again, we've got these tails at the end, which tells us that there's something not quite ideal about our behaviour. Okay, just to look at another example. Okay, you can see that there's not a huge amount of change then in the performance of our electrode after 1,000 cycles. A little bit. Okay, drop off again of the relative capacitance. You lose about 20% of your specific capacitance. Okay, and again with insertion times, there's no tilting, which is something again very positive. So this stuff was summarised. We had a paper out last year in Journal Materials Chemistry A, where you can look at this. We can get some very high specific capacitances. Okay, so close to 4,000 microfarads per square centimetre. I guess you guys probably don't work in this area. To give you an example, the best carbon-based materials are around 400, 500 microfarads per square centimetre. For ruthenium oxide, it would probably be nearer 8,000, but actually, this is pretty good considering the cost. So we were quite happy with that. So there we go. Quick summary of this. Okay. Our changing, we use electric fields to change the structure. We get improved wetting, and this improves our active surface, and we get a higher specific capacitance as a result. So a fine example of those structure property relationships working well. Okay, I'm going to very quickly say something about metal oxide gas sensors. Okay, why are we interested in these? Well, they're cheap. Most of the ways we want to detect gases will either involve optical sensors or electrochemical devices. Okay, they tend to be 2, 4, 5, 6 times more expensive. Okay, metal oxides will tend to be very robust. Okay, electrochemical devices will have their electrolyte dry up. Optical sensors need constant recalibration, and they tend to be quite delicate as well. Okay, however, we have some drawbacks with these. Okay, selectivity is a problem. Okay, just the same as with all types of chemical sensor, but probably a little bit worse, and that's a result of the mechanism of how they sense things. Okay, and they also have a relatively high power requirement, approximately 100 milliwatts. Again, depends on the application, but what you will not be using them for is remote sensing networks where you cannot go and replace batteries every day or something like that. Okay, anyway, so sensor build, what are we talking about? Okay, our sensors are based on this gold interdigitate electrode. Metal oxide layer goes over the top. On the back of our chip, there's a heater track which we apply current across, resistive beating, continuous current, you get continuous temperature. finished device looks something like that. This alumina chips area is about 2 square millimeters, so they're quite small, very tiny. And they work kind of like this. So you've got your metal oxide in an oxygen atmosphere. Some of the oxygen will absorb onto the surface. In a surprisingly thermodynamically stable reaction, you get some ionization to produce O2 minus and this kind of thing. Okay, because we've taken some electrons out of our conduction band for an N-type material anyway, we'll see that our resistance will change across our interdigitated electrodes. It will go up in this case. Okay, along will come a reacting molecule, carbon monoxide here. Okay, it will react with that surface species. Those surface species produce carbon dioxide. You see the electron goes back into our conduction band. So this happens for all of our species. Okay, we recover our electrons and we see that our resistance goes back to where it was in the first place. So this is basically how these things work. So any kind of combustion reaction you may detect. So typical trace for an N-type material then is you're in an oxygen atmosphere, you put your analyte gas in, okay, you'll see some reaction which is releasing those electrons which have ionized your oxygen species. They'll go back into conduction band, resistance will lower, and then when your analyte gas is removed from the gas stream, you'll tend to go back towards your baseline amount. So there's a few important characteristics. Probably the most important one, certainly one that we're going to worry about, is this Gash response. So this is just the ratio for an N-type material of the baseline resistance divided by the resistance of sensor in gas. Of course, you can get lots of other information about the speed of response and various kinetics and bits and pieces from the shape of the curve, but we won't worry. Okay, microstructure is super important in this case. Okay, now obviously, if you've got your materials like this, you've got 3 parts: bulk of material, the surface of the material where you can absorb oxygen and get these ionized oxygen species. Okay, now these are the parts which are going to react with any analyte gas, and it will only be this surface region which will contribute to the change in resistance or conductivity that you're measuring. Okay, grain boundaries then will just merely provide some kind of energy barrier for charge percolation through your network. Okay, you can get an equivalent circuit model, something like this. Okay, what we really want to do is maximize the amount of surface that we have so that we can have all of our material being active so we can get a much bigger response. However, the problem is if we do that, we make these grains smaller, it means we can have a lot more grain boundaries, so our baseline resistance will go up. And just keep that in mind. The operating temperature is also important as well. Okay, if it's not high enough, you won't have enough charge carriers in your conduction band. If it's too high, you'll just get heat desorption and hindered diffusion on your surface. Okay, again, not desirable. Okay, in this case, what we're going to do is we're going to make some tungsten and titanium oxide sensors. Okay, again, using these standard conditions, and we're going to change again our electric field strength. Okay. Now, rather than have our traditional cold wall reactor, what we're essentially going to do is put just a gas sensor chip which has got no coating in it into a metal tube and have our aerosol flow across the top. We're going to use the gas sensor's integrated heater to heat up to the deposition temperature, and we're going to apply an electric field across those interdigitated electrodes. Okay, all of the gas sensing stuff we do in-house. We get various different gases and stuff. It's essentially just a bunch of mass flow controllers, valves, and a bit of electronics which does some measurement. So if we look at the titania sensors we produced, again we can see that we've got some changes in the relative orientation or relative intensity of the different peaks of our material. These starred peaks correspond to the gold electrodes and the alumina chip substrate. Okay, all I really want to point out then is that depending on the electric field, okay, we might get a larger 004 peak than the 101 for our anatase titania. Okay, and we see similar kind of changes in our tungsten oxide as well. If we consider our film produced without an electric field, which is this one here, and then with a stronger electric field here, okay, you get much or quite different orientation changes with a different electric field strength. Okay, again, sorry, just some Raman spectroscopy then, just to show that we do in fact get the phases that we want. The titania, which corresponds to anatase, and for the tungsten oxide, that's quite nicely monoclinic tungsten trioxide. Okay, so what about functional properties? Okay, these are the surfaces of our titania. As we increase our field strength from A up to F, I've not got all of the details again because this has been IP protected. Okay, we see some strange changes in the surface, more surface texturing and a higher density in our films. Okay, and actually, well, for the majority of the films, actually, that's a highly undesirable thing. We get really not very nice sense results. But for some of them, okay, if we look at the Gash response to ethanol, you can see for our modified sensor, which is this red trace. Okay, if we look at this ratio for our Gash response, we get a bigger Gash response. We tend to get less saturation on our peaks, which is indicating that we have more active sites. So if we produced an ethanol sensor in this case, which is a little bit more responsive than what we can normally do. If we look at tungsten trioxide sensors, okay, you can see that there's a huge change in our structure. You normally will get from the deposition of this tungsten hexaphenoxide precursor these kind of anemone type structures. As you increase your field strength, you tend to get longer and narrower kind of nanowire type growths, and a disruption of this kind of almost tubular type of microstructure. And again, okay, we see essentially a similar kind of thing. This time to nitrogen dioxide. Okay, it's a different sort. It's an oxidizing gas this time. Okay, and one of the problems, of course, with producing nanomaterials, as I mentioned, you produce a lot more grain boundaries, and we see quite a lot of noise in our signal. Although one thing I would like to point out is that these are very, very good responses to these part per billion levels of this gas. So we were very pleased to see this. Okay, something very quick about photocatalyst. So we noticed that we saw this change in crystal structure. Okay, well, if we look at making these films now on glass, okay, we can see some microstructural changes. Okay, what we're going to do is we're going to look at some intelligent dye testing to assess the photocatalytic activity. We use this resazurin type dye. Okay, it starts out this nice blue colour. As it gets oxidized, it changes colour to pink, or through purple to pink, and then gradually goes colourless. This is something that was developed by Andreas Kafizas at UCL some time ago. It's very, very nice, easy to follow experiment. Okay, if we do this, well, what we can essentially see is we can see some massive decreases in the half-life, and these peak shapes are not what you would expect from typical first-order kinetics, which is the type of thing we expect. There is clearly several things going on. However, what I will say is the initial part of the curves can be very, very quick, and this is indicative of these films working well. So I think what we can say anyway is if you look at the 0 volt samples, this is a film made with no electric field, okay, and then you look at some of our electric field samples, you can see clearly that we have a much quicker destruction or oxidation of this ink. Okay, and actually this correlates quite well to these changes in this 004 or appearance of this peak of the 004. And actually there's been a couple of papers which suggest that this is actually a very good surface to have your charge on. I've lost the word in my head. It's to stabilize your electrons on, okay, to prevent recombination. So the fact that we can produce films which apparently have more of this surface available means that we can get better photocatalytic activity. Okay, so just there. Okay, we can make a bunch of these metal oxide films, we can change crystallographic orientation, and as the functional properties are linked to to this microstructure and this crystal structure, okay, we can see different functional properties. Okay, and we can tailor this microstructure to some extent. And just a couple of examples I've given you. Okay, we can make gas sensors with enhanced responses, photocatalytic films with apparently higher activity, and the various other bits on supercapacitors and whatnot. I'm really, okay, I want to go through the photovoltaic stuff. Okay, so general take-home message is that, you know, this is quite interesting. We can do some interesting things. I'm only at the beginning, really, of starting to do any of this, and I'll be honest with you, I don't understand completely how everything happens. And if anyone has any ideas, feel free to come to contact me and talk to me. I just want to end very quickly by going through some recent stuff we've been doing on photovoltaic, because I think some of you guys have been working on perovskite films and stuff like that. You might find what we've been doing a little bit interesting. So, well, first thing I'm going to talk about zinc oxide scattering layers. One of my students, okay, he noticed that, okay, if you get this increased scattering, you'll get better uptake and improved efficiency in your solar cell. So how can we make some TCO layers which have these kind of structures? Well, it turns out you can do it quite easily by adding acetic acid in. Okay, increasing amounts of acetic acid into the deposition, you can get these wonderful pyramidal type zinc oxide layers. So that's all marvellous. Okay, some of the haziest films reported without using any sort of etching post-processing. So this is really nice that you can just do this in one simple step. Okay, I also want to say something about dye-sensitized solar cells for energy-efficient windows. Okay, here's a lovely picture of the City of London. Okay, as I mentioned earlier, okay, we don't have the greatest energy efficiency for these buildings. Okay, what do we want to do? Well, we want to offer some solar control, reduce heat loss and whatnot. Well, what about if we can have our window also being a solar cell? Okay, we can reduce the solar heat gain because we can absorb a part of it. Okay, we're going to harness some of that solar energy because we're going to convert it to electricity. So we're offsetting some of the energy, and actually, compared to other building integrated photovoltaics, DSSCs are cheap and relatively simple to integrate, although they are not without their problems, as I'm sure you will know. And then, of course, depending on the thickness of our titanium layer and the type of dye we use, we can have some changes in the amount of transparency and the kind of colour that your window might be. Okay, so just to show, we've taken a bunch of different approaches to this using sol gel, aerosol CVD, and something called hybrid CVD approach. And here's an example of one of our little devices we've made in our lab, which has got a nice little green colour. That's the kind of thing which you can sell people because they don't mind green on their windows, but they really don't like yellow or brown. Okay, we're using a whole bunch of different sensitizers and natural dyes, different bunch of electrolytes as well, and a different bunch of inks. So far, power conversion efficiency of 0.005%. Okay, it's not so good. But actually, you know, if we could get up to about 0.5%, which I think is, it's 2 orders of magnitude increase in our efficiency, but I think it's something we can do. If we could do that, you think about the surface of a building, and actually the fact that you're absorbing some of that heat energy, and even if you're only turning 0.5% of that sunlight into electricity, that's going to make a massive difference to the energy demand of that building. But like I say, we've got a lot more work to do on this. This is one of my PhD students who's been working on it for about a year or so. I'm sure we'll do better as time goes on. Okay, final thing I want to mention then, perovskite layers. Rather than some of the stuff that I think you guys have done and Ivan Parkin's group have done at UCL, we've taken to a sequential CVD method. Okay, first reaction is to deposit some lead iodide and then have our methyl NH3 iodide in the second step. And the reason for this is we find that we get some nicer morphologies. Okay, so typically something like this. This is deposition on FTO. I'm not sure, Paul, if you've seen this. You may have sent some comments back to Chemcom.
No, I haven't.
Okay, and one of the things that we find is we get this nice porous layer, which means we'll be able to get some nice absorption on. However, we've still got numerous microstructural faults and cracks, which means that there can be some short-circuiting in our cell, which is part of the reason why I don't think anyone has shown a working cell, perovskite cell from CVD. Okay, so this is an FTO. Okay, it needs to be done on the zinc oxide layer really, because you need a blocking layer in your actual cell. Okay, here, okay, again we've got kind of porous microstructure, but actually much better coverage in terms of the kind of coverage of our film. And the results I got this morning, which is why I wanted to put this in, is to show actually we can actually now, we've just started, so my students just produced some of these things essentially with very minimal cracking. So by using this sequential technique, actually we can start to get these really quite dense but rough perovskite films on the surface of our this is on FTO, so we need to do this on zinc oxide. I was really pleased to see this, because this means that we've got the potential to produce a perovskite cell in an entirely online fashion, which means you don't have to faff around with all your solution processing and stuff like that. You can just have a plant to do it, which could be a massive step into making these things a reality. Well, anyway, okay, just to summarise then. AACVD, you can do some interesting things with PV. CVD can have an answer for virtually all aspects of the cell performance, and whether it's the scattering layer, the absorbing layer, the blocking layer, whatever. Okay. Okay, maybe we can use DSSCs as energy efficient glazing as well, possibly. Okay. And yes, maybe we have this online route to perovskite PV. But of course, as always, more to do. Okay, I just want to finish by thanking all of these people who I've worked with for the last however many years it's been. It's impossible to name all of them, what I've done. I think the final thing is to say thank you to these guys, because these various companies and research councils that have given me money. Without them, I couldn't do anything. And finally, thank you for listening. And if you have any questions. So I apologise, I realise I've whipped on quite a lot there. Yeah.
Your glazing, when you do oxides, how durable will the films be if you are continually changing the structures? So relatively crystal to...
Okay. The answer to that is not something that we've looked at. It's something which I can't remember which group did it in the mid-90s. They did cycling 3,000 times, and they found there was no issue with delamination or anything like that. However, vanadium dioxide is not a particularly hard metal oxide, and part of the reason why in our model we put it on surface 2 is because there is no way it could be an exterior surface. It would weather off of a glazing panel really quickly. It wouldn't last there. So actually the transition is quite durable for thin films, not for the single crystals. They tend to crack after 2 or 3 cycles, but for thin films it's been shown that they're quite good. Yeah.
I'm struggling to work out something. My physics is letting me down. It's something to do with, if you're working at 30 volts, that's about 300 volts a metre or something, isn't it?
I think with a 1 centimetre gap, which is what we typically have, it's 3,000 volts per metre. Yeah.
So how does that, what's the kind of energy of interaction of that with, say, something that's got a normal type dipole moment, say? If you took a molecule with a dipole moment and say it had a debye on it, which is something which comes out of something like
Oh, good Lord.
3.33 times 10 to the minus 30 coulombs per metre, I think. And I was trying to work out what the interaction energy was between the two. I thought it would be quite an interesting thing to do.
I agree.
I didn't think it'd take too long. I actually thought I could do it while you were talking.
I'd not really considered it, to be honest. I think it would be something.
Because the other thing was in your vanadium oxide thing, I think it's vanadium oxide, where you had the interesting phase change. I was also trying to look up the phases, because you could imagine in a system where you've got various phases that you could favour phases that are piezo or dielectrics over ones that aren't. So it might be interesting, for example, in growing Oh, what are they? Is it lead, strontium, titanate?
Yeah, some of those
There's
things.
quite a lot of interest in those.
Or
Styrene
lithium nionates.
Yeah, lithium niobate.
Or zinc oxide as well, actually.
PZST, isn't it? Is the one that they
Yeah.
use in night sites. Yeah. And I just
Yeah,
thought maybe there could be an interest there, because if you, I would imagine you could improve the figures of merit by pulling the things into the right orientation. You've done zinc oxide, have you?
Not with electric fields, no. That's on the agenda.
I mean, that's I know you have to zinc oxide somewhere, but it was often flat. Because the big emphasis in zinc oxide is often making these pillared structures, which you can make by a variety of methods.
Yeah.
And I always thought that would be good and easy to do, because you could do it from zinc acetate in your system.
Yeah.
All you have to do is dissolve zinc
Well,
acetate.
it's normally done through growth of the sealing layer hydrothermally.
Yeah.
Or maybe not hydrothermally. That's not. But yeah, under quite mild solution conditions.
But you can make it do clever things. You can make lasers.
Oh yeah, or energy generators. Yeah. Well, like I say, it's on the agenda.
The other thing is you want to get lots of citations published on zinc oxide, because you get 10 times more public citations than zinc oxide, because it's a big community in any other area of material science.
That's something to
do.
do. But actually, thinking about the interaction energy, I think it's probably quite important to look at it, because one of the criticisms I get is, well, we've got all these other things like plasma CVD. It's kind of like, you don't have a plasma. You're not making a plasma. It's quite different. The sort of voltages you're talking about, the electric fields you're talking about, are really quite different.
Because that early slide was quite interesting, because what it looked like was you were getting quite a small shift. I actually did think it was analysable. You said it didn't. I thought you could have got some stats out of it. And then
we've got some numbers.
Yeah.
I'm just not confident to come and tell you what they are, because I recognise that the error in them, because we don't have enough peaks to really.
You really will need thermodynamics, because you've got a KT number that's determining the tunneling, right? And then you've got an energy which is trying to overcome entropy in a way. It's actually really interesting.
Yeah. Well, one of the things that we've been trying to do is to get EPSRC to give us. We're all trying to get EPSRC to give us money, but to do some computational studies, do some kind of molecular dynamics and computational fluid dynamics stuff, to try and look at some of these things on an atomistic timescale and length scale, to see what we can.
I think you make quite a bit of progress with a bit of paper, actually.
Well, that's the other option, of course. Yeah.
So, I think you could actually. But there's quite a Unix problem. It defeats my memory of electrostatics, because I think the answer is a simple one, but I couldn't work out how simple. It's very interesting. I mean, I would have thought that piezo and pyroelectrics. I'd be happy to collaborate on that, because we had systems that you could put them down at plus under 500, which is quite accessible. Which it's never really been developed actually, because we closed down all our facilities for doing it in the UK like we usually do.
One of my colleagues, Steve Dunn, he's big into his piezoelectrics, usually by solution methods. But we
find that a lot of the CVD work is kind of done at 700. You can get down below 500, which is the kind of working temperature with the device. Very nice.
Well, we've got a PhD student starting in the area of zinc oxide anyway in September, so we can always make their projects a little bit broader.
There's quite a bit of stuff on zinc oxide.
Yeah.
Very good.
Yeah, cool. Sorry? The temperature limit? That's a good question. I don't know. I think we've only ever looked up to 600 degrees, because much beyond that our glass will start melting, and that's messy and unpleasant. And I think that the other issue we have is if we start using steel or some kind of metal substrate at higher temperatures, you actually have a much bigger fire risk actually. So it's not something we've ever been keen to do. But actually one of the things that we need to look at is how does the conductivity of our substrate change at different temperature, because that will of course impact on the strength of the electric field. Because I mean, I'm presenting all these numbers and they're saying, oh, we're applying 30 volts potential difference. I've not said what the electric field strength actually is, and that's partly because I don't really know, because I'm not quite sure how temperatures will change the, your whatever, your permittivity and whatnot. So I think Paul's right. Actually, we need to sit down with a pen and a bit of, or pencil and a bit of paper and actually.
I think that one where you were seeing the
do a bit
shift
of maths.
voltage was quite interesting, because I reckon you could plot something. I'm a great one for plotting things. And I do think you could plot sort of some shift in that peak against voltage, and it looked almost as though there was a catastrophic phenomenon.
Yeah, it looks like you get gradual, and then it just kind of stops.
It's quite common.
Mm. Yeah.
Using oxide and against manual oxides. So we tried just a simple acetate salt in water.
With the electric field stuff, not really, but most of that is because making a decent aerosol with water is a bit problematic. Well,
You could get zinc acetate.
you can.
50-50 ethanol water.
Yeah.
That would probably make an aerosol.
Yeah, I mean you can do it, but
The
I
other
mean,
one
I
is to
think-
use basic zinc acetate, which is the zinc
Yeah.
zinc acetate.
No, I think I mean definitely you can do these things. You can make aerosols from water, but with the kind of piezoelectric generators, humidifier things that we're using, it's we tend to want to stick to alcohols because they're much easier to produce a good mist.
I think basic zinc acetate is quite soluble in alcohol, and it's dead easy to make.
Well, like I say, with the guy we've got starting in September, he'll be doing a lot of zinc oxide stuff. You don't get too many zinc precursors, which are, well, most of the freely available and cheap ones are only really soluble in water. So
We published that, so have a look at it.
yeah,
We published it 20 years ago. Some other things,
they can have a fun
Zinc
literature
oxide
search.
comes around. You must publish on zinc oxide. You get
Yeah,
hundreds
no, I
and hundreds
know.
of citations.
It's this kind of cyclical nature of everything, isn't it?
Zinc oxides are ridiculous.
There's very little new under the sun, but we keep rediscovering it.
But you publish enormous papers on things, and nobody reads them. You publish a fairly indifferent one on zinc oxide, and you look 2 years later, 50 people have cited it, don't mind read.
Not a bad plan. Okay.
So we'll be hoping some of the results.
But if you want to do something more serious, we can talk about that. I'd be quite interested in something in the piezo-pyroelectric field.
Yeah, no,
It'd
definitely.
be very interesting to look at, because it might all align the right way. There's no one left in the UK who looks on it.
Well, that's very good.
Anyone? I think that's it then.
That's very nice.
Yeah, I mean it's.
Yeah,
I think one thing we can show beyond doubt is that applying electric field